Recording will start soon, it says.
Can the folks online hear us okay?
Yes.
Okay.
Perfect. Very good. Okay. Thank you all. Thanks for coming. Today we have a EOL engineering seminar by Professor Sunil Khatri. This talk is about the flash, which is a floating gate technology or floating transistor technology, however you call it, called the flash in short. And he'll be talking about non-volatile design using the flash technology for analog and digital designs. Professor Khatri is from Texas A&M with 33 years. He works on computer design, computer architecture, digital circuits. That's his experience. Plus, he worked in Motorola for 4 years on 2 of the FPGA design teams. So he comes from Berkeley, where he did his PhD. He was in CU for briefly, then moved to Texas A&M. 33 years of teaching experience with a number of proposals and students and number of patents here. We thought it's really good. You can interact with Sunil. At this point, call me Sunil if you want. On some of the digital designs here. That's why he's here. He's an affiliate faculty. That term is for 3 years. He just started 3 months ago. It's a first visit, trying to get his feet wet, do some other work here. But he's not a newcomer to UOL. How many years ago? About 15 years ago?
17.
17 years ago, Sunil offered some of the FPGA programming classes here. Many of them took here, and the first 2 radar down converter based on FPGA design was done under Sunil's guidance here. So Eric could add to it. Before that, what were you using? Microprocessors, radar?
We were using just this DSP chips.
DSP chip.
Yeah.
It's all converted FPGA after this course, and we got comfortable with that. That's how we moved on to 2 of the down converters and that for radar design. That's my brief introduction. He has a lot of papers and easy to work with. And being affiliate scientist, we have access to him anytime as we need it, and he can also visit when we wanted him to do it. Okay, with that introduction, Sunil, go ahead.
Thank you. Thank you, Vic, Eric. So basically, what I'll talk about is something that started about 7 years ago. It started almost by accident. So I had the opportunity to learn a little bit about Flash. And Flash is a floating gate technology that's commonly used for memories, right? Non-volatile memories. So SSDs, solid-state disks, and thumb drives, and so on use Flash technology. So I learned a little bit about the circuit parts of the flash transistors, and I said, wait a minute, this is something that can be applied in more general applications, not just memory, but non-memory applications. And that started something like 2016, 15 or something like this. And then, there was the first papers we did on that. And then since then, it's just been a lot of papers. So I claim that Flash is in some sense a forgotten technology. We've really not leveraged it for anything more than, non-volatile memory. And in this talk, I'm going to try to show you what all we've done with Flash that shows its utility in non-memory applications, lots of them, by way of lots of papers, by way of collaboration with lots of, students and colleagues. So before I start much further, I'll acknowledge co-authors. There's Sarma Mridula, who's from Arizona State University, a professor there. And, some parts of this work, we worked collaboratively. And then the rest of the names in this list are my students. Mondar is the first guy who did the Flash-based work. His PhD thesis was on the use of Flash for digital designs. And then there's Kunal, who did some of the security work. Xiaowei, who's currently attending also, and he's done some of the secure Flash-based work. Zhengyan, who's done a lot of the analog Flash work, he's also attending in this room, in this meeting. And then Kyler Scott, who's done a bunch of other Flash work, he's probably not attending. And then Gyan Singh and Ankit, who are students of my colleague Sarma from Arizona State. Any questions, contact, comments, etc., by all means, feel free to contact me. My name is Sunil Khatri. My email is just the first name followed by last name at tamo.edu. Easy enough to remember. All right, so let's see how this all goes. Now, the reason we're looking for better ways to do chip design is that there's this thing called the Moore's law, which is basically being eroded or slowing down. So Moore's law is, genetically, loosely speaking, it said that we had the ability to make chips double in complexity every something like 18 months. And the mechanism for doubling complexity was making transistors smaller. And so you could squeeze more transistors in the same chip, and then you could get more complex functionality and stuff. But the problem is that Moore's law recently, even 10 years even, right, has been significantly degraded, right? So what's this degradation coming from? It's coming from things like lithography issues, the ability for us to design chips and fabricate them with features that are precise has been significantly eroded. So lithography issues have contributed to the degradation of Moore's law. Then processing variations. When we want a certain width of a metal, when we want to dope silicon a certain way, the actual doping we get is never exactly what we want. And that gets aggravated as the feature sizes or the transistor sizes get smaller. Then comes more recently, there's things called, aging effects, right? So over time, a chip starts degrading. So it starts to get slower over time. And so if it gets slower, if you use it after 4 years, and it's no longer fast enough, you got to toss it. And then crosstalk related issues, wires that are too close to each other can have capacitive crosstalk coupling, influencing each other's sort of voltages and stuff, causing errors. So all of this degrades the ability of our ability to design chips reliably. The interesting thing is many of these physical phenomena, they all can be modeled mathematically as a change in something called a threshold voltage of a transistor. The threshold voltage of a transistor is the voltage at which the transistor just turns on. So a lot of these effects manifest as VT changes in terms of a mathematical model, like a SPICE model. So the question then we can ask is, irrespective of what effects are going on, can we, after the fact, can we get a knob that allows us to change the VT and get it to where exactly we want it? So in an ideal sense, let's say I wanted a specific VT, do I have some knob which will allow me to adjust the VT after all these effects are going on, so that I get the VT I want and I'm off to the races? I basically erase the effect of all these variations, right? All these things that were holding me back from designing chips, can I sort of adjust for them with a secret knob? And the short answer is we had this secret knob in front of us all along, right? It's in the flash technology. So, but we've never really used it. So let's see how that all works. Now let's talk about this threshold voltage for a slide. Let's talk a little bit about what it does and how it works and where the problems come from and how flash erases them, if you will. In a normal transistor, right? Perfect transistor, let's on the y-axis, I have a current through the transistor. And on the x-axis, I have the voltage I apply to the gate of the transistor. So if I apply a voltage which is past a certain value, the transistor starts conducting. As you can see, so this is basically the ID VGS curve of a transistor. Yep. And this magic voltage at which conduction starts is called the threshold voltage VT. Good. All this is good so far. Again, like I said in the last slide, because of all those variations, lithography and so on, this VT varies all over the place. So when I fab a transistor, like out of the billion transistors in my iPhone chip of several billion, I can never predict what the VT of a certain transistor will be. So there's all these variations among these transistors due to those effects. So the VT I get for one transistor randomly varies. There's some distributions that we have and so on. But this is something we don't want. I'd love to have a single VT. Can I do that? Is a question, right? And flash lets me do that. So if I have a flash transistor, which is also a transistor, it has the ability to change the VT by trapping electrons in this floating gate in the flash transistor. So when there is a mechanism, I'll talk about it shortly, by which I can erase the flash transistor. And erase is a synonym for making its VT negative. As you can see here, the VT, which is the point at which it starts conducting, in this curve on the right, is negative. So erase gives me a negative VT. But then I can also program the flash transistor and alter the VT. Let's say I want the VT to be at the spot here, which is designated by that yellow curve, right? So I can program the flash transistor, which changes the VT, moves it to the right a little bit. It's still not where I want, so I program it with another pulse, then move it a little closer. Every time I write, I'm checking, right? How close am I, right? And finally, I get to the VT I want, and now I've dialed it. I have this knob which dials in the VT, the exact VT I want, which is powerful, right? Which is significant here. So this VT, by the way, I can dial with a granularity of 2 millivolts, which is insanely small, right? So this allows me to get exactly the IV curve I want. And this can have a dramatic impact on integrated circuit design of all kinds. So what kinds of ICs does this help? It can help, and we've explored as well, various kinds of ICs like logic ICs, analog ICs, and algorithm accelerators and stuff. And in the yellow parentheses are the papers that we've done, and there's some that I'm missing here, right? So essentially, you can exploit Flash to design, logic ICs, like your iPhone chip, if you want to think of it like that. We have 2 approaches to do that, and I'll discuss them briefly. And then also secure ICs. We'll talk about why we are interested in secure designs and how you can do them with Flash. Also, analog ICs, we can do FIR. We've published papers for FIR filters and also voltage regulators, DC-DC voltage regulators. Currently working on FFTs as well. And Chen Yan, who's in this meeting, he's working on that. And Xiaowei is working on the Flash-based secure logic there. And then also algorithm accelerators. So we can do all these. The yellow ones are the ones we've published. There are a few more papers which I won't cover in this talk. Now, what benefits can we get for that? Like I said, the first benefit, right, which we already talked about, is a precise control of the threshold voltage, which allows me to manufacture the chips with precision. So the yields will be much more. But even better, the manufacturer can control the VT and therefore the speed of the chip. And so they can sell the chips at the faster chips, which they can select, let's say 20% of the chips to be faster. They sell it at a higher price. The other chips, they sell at a lower price. So they can tune the speed binning, and that's how they sell more and less expensive parts, right? But now you can control the speed binning. Traditionally, speed binning was something that they were at the mercy of the variations, and they get to speed bin based on it. The additional advantage is I can erase the VTs and reprogram them in the life of the chip. Let's say the chip is aging and it's getting 6 years old or something, and it's slowing down. I can reprogram all the VTs, and now I've mitigated aging. This is something with traditional design we simply don't have the ability to do. And also, when we do all these designs, as you'll see in the results, we get significantly better metrics like delay, power, area, energy. These improve dramatically compared to traditional designs. And these comparisons are with, industrial tools, right? Like the tools you use for the industrial design. It's rare for something like this to have the ability to beat traditional designs, which have been tried and tested and beaten down for like tens of years, right? So it's rare for a new technology to show up and be that, and be able to beat the traditional CMOS so much. Of course, the gains will depend on the application, as we'll see in this talk. So there's a lot of promise here, right? And in the rest of this talk, right, I'm going to talk about evidence of this promise by way of papers that we've done. And of course, this is a short talk, so I won't be able to cover everything that we've done in this space, but I'll sort of give you a flavor for many of these topics. Now, the first thing, the naysayers, a lot of times people, when we write proposals and papers and stuff, the reviewers might say certain things, and I kind of want to sort of come up with their questions up front and address them, right? So the reviewers often will say, well, but flash transistors have a finite write endurance. So we all know that, right? Like the SSDs have a finite number of times that the SSD can be written before it's no good. That's true, but that's a problem for memories. It's not a problem for us because, as we'll see, we program the device only a handful of times. Once in the factory when it's programmed, and the next time possibly when you're mitigating aging and we're reprogramming things. So we basically program the transistors at most a handful of times in their life. So we're nowhere near the 100,000 write limit that we have for flash. The other is the memory folks have this standard problem, which is something called read disturb and write disturb for memories, which basically alters the state of cells when you read or write other cells. Again, this is not a problem in our design because we write very infrequently. And also, the transistor stacks in our design are very shallow compared to flash memory. So all of this reduces or diminishes or eliminates the problems that traditionally are faced by the flash-based memories, right? Because we're not doing memory, we're doing like logic designs and analog designs. And also, flash has always coexisted with CMOS. In other words, when people do a flash memory chip inside your thumb drive or your SSD, that flash memory chip has on the same die, CMOS and flash coexisting. They fabricate well together. They sort of live on the same chip together perfectly well. So that's never a problem, right? In our circuits that you'll see, I use CMOS and flash together, but they can reside on the same chip. They don't have to be on two different dies which would have made things hard. All right, so this is basically the outline of my talk. I'll quickly talk about flash transistors and then, some approaches which talk about how we do better digital designs, and then analog design, and then algorithm accelerators. And by necessity, I'll go through all of these somewhat briefly. If there's further interest in any of these, I'm happy to talk some more. All right, a flash transistor is a floating gate transistor. So you can see that this is a traditional transistor, but it's got this extra layer which has a bunch of E's written on it, sandwiched between the substrate, which is at the bottom, and the gate, the control gate, which is at the top. This floating gate is, as the name suggests, floating. So it's basically high impedance, nothing contacts it, right? And so if you trap electrons, that's what I've indicated by those little E's. If I trap electrons in that floating gate, they're there forever, literally for tens of years before they escape, right? Or before they could come out. So there's this floating gate, and I can inject electrons into this by something called Fowler-Naudin tunneling. This was invented at Intel, right? And I can also remove them by FN tunneling as well. So I have the ability to inject and remove electrons into this floating gate. And once they're there, they're there. So when they're there, they alter the threshold voltage of the transistor. Remember, we said we wanted to alter the threshold voltage precisely. Well, that's the mechanism. The FN tunneling is what allows me to alter the VT, because the absence of presence of electrons here manifests as a VT change. The other good news, right, which is something that our results illustrate, is in a traditional transistor, there's no floating gate. So the actual gate is much closer to the substrate, i.e. the gate capacitance is larger because of the distance being small, right? So capacitance is inversely proportional to distance. But in the flash, the control gate is much far away from the substrate. Therefore, the gate capacitance drops, and that gives rise to faster switching. And that is something that our results show. So it's much faster, than a traditional transistor by dint of the fact that the gate is far away from the substrate. All right. Historically, as I said, flash has been used for memories, but never been implemented for non-memory circuits. That's kind of what we are sort of, excited to do. Okay, when we program, there's this first step called erase. Erase basically brings the flash threshold voltage all the way to the lab, which is a negative threshold voltage. It's done. I mean, the mechanism of doing it is shown here. Like you drive the control gate to ground. And I won't go into that. It's a well-known mechanism, nothing new here, right? But in the process of erase, the electrons tunnel into the substrate, so they leave the floating gate. So the floating gate is devoid of electrons at the end of this. Now, let's say I want to program this to this VT that's shown by the dotted line. The way I'll do the programming is by inserting electrons or injecting electrons or tunneling electrons into the floating gate, which would result in an increased VT. But I want that precise VT. So how do we do it? The mechanism to do it is to drive the control gate to something like 20 volts, ground all the other terminals, and then apply a pulse. Every time we apply a pulse, we get a little bit increase in the VT. And then we'll do a verify. Has it reached the dotted line yet? So it's no. So all right, apply another pulse. This time a little smaller, get closer to the VT we want. And then as progressively the pulses we apply will be thinner and thinner until we get our VT that we wanted dialed in. Right? This VT can be controlled precisely, like I said, to the precision of a handful of millivolts. All right, using all this, we'll now talk about some of the ideas we've explored with, to do digital design to start with. And there are two methods for this. So I'll talk first about method A. These are the papers that were sort of done for method A. Method A was the stuff we started with. So it's the first papers are 2016 and stuff, right? These were the part of the PhD thesis of Mondar, who was one of the authors of this paper. Actually, we have a position paper we published in one of these book chapters recently, right? Just says like, hey, we've all forgotten about Flash. Literally, the title is the same as, the forgotten technology and so on. Just trying to like sort of drum up some interest in this thing because this has just been sort of ignored, I think, for too long. All right, in this Flash-based method A, let's say we have a traditional design on top. What we'll do is we'll cluster the gates of that design, the little circles are the gates. And these clusters are like cluster A, cluster C, cluster D, and so on. So what you see below is the clustered circuit. Now, each of these clusters of gates, we'll implement using Flash, and we'll call that literally a Flash cluster. So Flash clusters are interesting because they can implement any function of a certain number of up to a certain number of inputs and up to a certain number of outputs, which let's say we call M and N. So FMN means a Flash cluster that implements functions up to M inputs and N outputs. In our work, we used M and N of 3 at 6 and 3. So you have a 6 input function up to 3 of them you can implement in one cluster, just one shot, right? So if you look at the structure of each cluster, if you had 3 outputs, you can see that you have 2 raised to 3 of 8 minterms. So each of the minterms of this are implemented in something we call an FLA or a Flash logic array. A small array to implement each of the possible 8 minterms of the output. And then the output generator sort of combines them and produces a certain output. So if you looked at that, and if we laid it out, if you look at the layout of it, you can see how deadly regular this is. And regularity in VLSI is always our friend, right? Regularity makes for, predictable capacitances, predictable parasitics, and so on. So this is a very dense, very packed layout. And, all these Flash clusters are going to be pitch matched, so they're easy to sort of put together in a larger circuit. When we put them together in large circuits, so this is several benchmarks, and traditionally in our field, right, we take, we evaluate these things by taking a bunch of benchmarks, which you can see on the left. These are large benchmark circuits that everybody in the field uses for evaluating their approaches. And then what we did is we implemented them in traditional CMOS with industrial tools, state of the art, and then implemented the same with Flash. And you see the last row here that shows the ratio of, for example, the CMOS delay versus the Flash delay. So our Flash delay is 60% of the CMOS delay. We're about 40% faster. That's kind of insane, right? That's a really large improvement. We also win in power. So the power is about 65% lower. And then you also see where the area is about 60% lower. I guess you can't see that too clearly. I don't know if I can make this. Oh, yeah, like that works. I can do that. So you can see where, the delay was about 60% larger on average over all those large designs. The power is about 65% better, and the area was about 40% better. So we did pretty good, right? Now the question might come out and say, come on, this just sounds too good, right? So for those who think this is too good, right? The question is, why did this happen? And the why is, the answer is what I alluded to earlier. In a traditional CMOS transistor, the gate is separated from the substrate by about 1 nanometer. But in a Flash transistor, the separation is about 20 nanometers. In other words, the gate capacitance is 20 times less. And that capacitance is always a dramatically large contributor to delays in chip designs. Smaller capacitance, smaller RC delay, therefore, your circuit ends up being faster. And that's essentially why we get this small improved delay. The other cool thing is we did a bunch of Monte Carlo simulation, and I'm going to zoom into this Monte Carlo. I hope you can see it, right? I think it's about as tight as I can zoom in. So here we took a design, implemented in CMOS, that is traditional industry circuit design methodology, and found the variations of the delay, which is the x-axis, right, over the Monte Carlo runs. Does that make sense? So you can see that the Monte Carlo delays are shown here. with flash, I have two histograms. There's a blue histogram, I think, well, the one on the right and the one on the left. Okay. Two observations, well, three maybe. One is the width of the histogram of the traditional is much wider. In other words, the delay variations are much larger. So if I want to spec a design, I have to be conservative and take the worst case delay, right? Whereas if you see the histogram widths of the flash design, they're much, much thinner. So we are more precise in our delay. That's one. The second observation, of course, is both our flash designs or both our flash implementations are much faster than the CMOS. As you can see, the histograms are much to the left, and that means they have a smaller delay. But yet further, with the same design, I can change VTs and I can pull in its delay from this one histogram to the left histogram. By adjusting the VTs and making the VTs smaller, I can make my design faster. And this is evidence that aging mitigation can be done in our design. I can take a flash design that was slow, reprogram the VTs and pull in, make them smaller, and now I have a faster design again. So this plot it shows a lot of things, right? It shows that we have a tight delay control, much faster delays, and that the delays can be adjusted, and we have a knob to actually control the delays of our circuit. All right. Method B, this is something we did with Arizona State. This was over my sabbatical, which was in 2019, just before the pandemic. And then when the pandemic started, I ran back from Arizona to Texas. I didn't want to be, stuck in a different town. Anyway, so these are a couple of papers for this thing. So this is based on the use of something called threshold function. So we'll quickly talk about what a threshold function is. Threshold function is just a function, a Boolean function that can be expressed by this algebraic property. So its output y is 1 if this sum is greater than a threshold. This sum is some weighted sum of the inputs of the circuit. These inputs are binary value, zeros and ones. The W's are weights. So if WIXI summed up to the n inputs of my circuit is more than a threshold, then the circuit's required to be a 1, otherwise it's a 0. This is just a mathematical construct of a Boolean function. Now, the parameters of interest are the weights and the threshold. So we can equivalently express this as an array of weights, WI to W1 to Wn, and the threshold that fully expresses the function. We draw the cartoon of the function just like this. We say this is a threshold and then apply the weights and the inputs. And this is sort of a cartoon that people conventionally use for expressing a threshold function. Now, the good news is many common functions that occur in digital design are threshold. So for example, if you have a function f, this is a Boolean function f, AB, on A, B, and C, the binary inputs, which is C or AB, you can express it as 2C plus A plus B greater than 2. So when C is 1, then this inequality is satisfied. The output's got to be a 1. But if A alone is 1 or B alone is 1, then it can't be the output is not a 1. But both A and B, if they're both 1, then the sum on the left becomes 2, and therefore the functions are 1, right? Now, again, if we were to express it as our tuple, it would be the weight of C, which is 2, weight of A and B, which are 1, and then the threshold of 2. So this function is expressed as 2, 1, 1, 2, and that's the same as a function A, B, or C, right? Interestingly, okay, most of the functions that we use in chip design are threshold, right? So when you do your chip design, the gates that are used in your chips, in your iPhone or whatever, right? Most of them, 70% of them, are threshold functions. So there's a lot of opportunity in some sense to implement them somehow using Flash. Well, how are we going to implement them using Flash, right? That's not completely obvious. So so far, all we studied is this mathematical construct for something called a threshold function. It's a Boolean function. I haven't made any connection of that with a circuit using Flash that implements it. Well, that comes next. So this is our little circuit that implements a threshold function up to 5 inputs, right? We call it an FTL cell, Flash-based threshold logic. So using Flash to implement a threshold function. And the circuit for this is shown here. I won't explain it in great detail, but I'll briefly talk about it. You see that these transistors here with 2 lines. the thicker lines, I guess you can see the two lines, labeled V1, etc., are flash transistors, the top row of transistors. The lower row of transistors are connected to the inputs X1 through Xn. So if X1 is 1, then the current flows through that stack, but the current is modulated by the weight for that transistor, which is implemented in the flash transistor. Right? So essentially, this structure accurately implements the threshold logic function. And this structure is the same for any threshold logic function. So any threshold logic function, I'll use this structure. And just by programming the flash transistors, I'll be able to implement any weight tuple that I want. So the same exact structure can implement lots of functions. In fact, the number of functions it can represent for 5 inputs is in the little less than 100,000, right? That's a really large number of functions. How do we use this in the big picture? The big picture use case of this is, suppose I have a circuit on the left. This was the original design. What I'll do is I'll identify in the original design threshold functions. And these are threshold functions that are rooted at the output, like here. This little blue looking cone, I guess, which is labeled A, is threshold, let's say. This other function here labeled B is also threshold. So these are threshold functions I identified at the output. Similarly, I could identify threshold functions which are rooted at the input, like that might be P here or Q there. So there's a CAD step that identifies these threshold islands, if you will. Simple step, not extremely complicated. And then what we'll do is we'll replace these islands that we identified, islands which we labeled A, B, C, and D, by flash transistor threshold logic black boxes, the circuit we saw on the last page. So this A gets replaced by this black box, the B gets replaced by a black box, and so on. The P and Q get replaced by the black box as well. And then all we're left is this traditional design C, which we'll re-implement because the black boxes are faster. So this is essentially what we do. The identifying of outputs, which are threshold functions, we term it as hybridization. So A and B are instances of hybridization at the output. So we call it output hybridization. And P and Q, P and Q are instances of hybridization at the inputs. We call that input hybridization. So in this work, in the first work we did, we only do output hybridization. Input hybridization is done subsequently. Here's the results that we get. Essentially, we used industry tools all the way, identifies these threshold functions and replace them by FTL cells. And then we say, how well did we do in this new design? So we had the original design, and then we replaced it with FTLs only at the outputs, and said how how much faster or better did we get? And you can see we did pretty good. Oh, you can't see that. You can't see that. You can see we did pretty good averaged over 5 really large designs, which are admittedly arithmetic designs. We got an area improvement of about 30%, power improvement 17%, wire length improvement 19%. This is ISO delay. We kept the delay the same, right? So this is pretty significant. This is something that's rare to find in some sense. Again, where did this improvement come from? It came from 3 things. One was we were careful to choose FTLs which replaced logic cones that were high in delay. So we were very cautious in choosing, carefully choosing the FTLs that we replaced. Also, as I've said earlier, the gate capacitances of flash transistors are 20x lower. So many of these FTLs are much faster than what they replaced, right? And then finally, the designs are fed in a behavioral description. So the synthesis tool has the ability to do further optimizations as well. So this is essentially our first set of results. Then comes the second method, the same method, but this is something we augment for security. This is work that Xiaowei, who's on the call, has worked on. So this is a paper we've just submitted. here's the idea or the motivation behind this work, right? First of all, today's IC manufacturing has a global supply chain, correct? And, often what happens is design, fabrication, testing, packaging, all happens overseas or in different countries. So once I create a mask to send a design, which I send off overseas to fabricate, I have little control over, if features get added into that or if features get inferred by the person doing the fabrication. People might reverse engineer what I sent them. So, and this is a big problem, right? So its estimated revenue loss is in the tens of millions of dollars, billions of dollars for people stealing IP because I sent them the IP to manufacture. They can modify or adapt it or reuse it or modify it, and that's kind of problematic as well. So there's this big IP protection challenge, which is there a way that when I send my chip overseas to fab, can I hide the functionality of what I'm sending so that when it comes back, I can apply some changes to the chip I get and achieve the function I want, but the foundry entity cannot do that. The foundry entity is not able to reverse engineer my functionality. So the question is, can we use our method B for this purpose? And the answer is yes. We'll go back to that cartoon which expressed where we showed method B. We had our original design, identified threshold functions, the A, B's, the P and Q, and then replaced it by FTLs. Well, if we do this like crazy, right? Every opportunity I get, if I replace by a sub-circuit by an FTL, guess what happens? The adversary who's fabricating this just sees 4 black boxes. They don't know what functionality is in that black box. But when I get the chip fabricated, I program these 4 black boxes and then the chip does what I want. But the adversary has no idea what was in the circuit I gave them, right? So this is essentially the strategy, right? These, like I said, the black boxes are programmed after manufacturing, so the foundry has no idea what was in them. And now, in this situation, right, I want to maximize the number of black boxes. I want to go nuts with the black boxes because the more black boxes I have, the harder the reverse engineering is. So in this process, in this flavor of design, I'm going to do hybridization of the inputs and the outputs. Hybridize as much as I can, right? So that's kind of what we'll do. Summary of the results. First, I'll explain the experiment a little bit. So Jacquie did the CAD tools to do input and output hybridization. And now there's a histogram of choices of these functions. Some functions occur very often and some don't. So we flattened that histogram again, making the adversary's job harder because the adversary realizes that I'm going to choose functions with equal probability, again, making their reverse engineering job harder. We tested this out on 19 large designs, did 2 experiments. Experiment A, whose results are on the left. Oops, I guess I should zoom in a little bit. On the left of this table, and then B are on the right of the table. Experiment A is for minimum delay. Experiment B is for an average improvement. Emphasis on delay, power, and area. And then finally, we have some numbers on the rows L0 to L11 that you see. Li means only choose FTLs when the threshold functions have I or fewer literals. In other words, I or more literals. In other words, the smaller the I or the smaller the L, the more liberal I am in accepting a threshold function, even if it results in a greater delay. A larger L means I'm going to be a little more selective in using my threshold functions, right? It'll result in fewer threshold functions, but a better delay. So that's kind of the trade-off. Now we have one number which expresses how well we did. We call this the metric, which is the base 2 log of the number of guesses it would take the adversary to discover my function, right? So if it takes my adversary 2 raised to 260 guesses to discover the function, the metric would be 260, right? Now, it so happens, by the way, that the number of atoms in the universe is around 2 to the 260. So if I do 2 to the 260 if my metric is around 260 or better, I mean, the difficulty for the adversary to hack my circuit is as bad as counting the atoms in the universe, right? For them. Okay. So as you can see now, for L0, our metrics are literally in the 2000. This is 2 to the 2000. This is insanely hard to reverse engineer. But even for L9 and L11, the metrics are healthy. I mean, 2 to the 200 difficulty of reverse engineering. And if you look at the design, if you look at the improvements, right? With L0, we have an area penalty, but that area penalty starts to decrease as you get to L11, right? So because we're using less FTLs. Because we're using less FTLs, we get a smaller metric, but also we get a better, area penalty. So this is basically, a pretty, in some sense, if you look at L11, there's no penalty in area, no penalty in power, there's no penalty in delay, but you're getting security, and that's a pity. So for all these existing security circuit approaches, they have a huge penalty in one or the other. And despite that, security is so important for defense purposes that, defense people say, well, we'll take it anyway. But this is sort of significant because there is no penalty at all for L11. You can see there's no area penalty, no delay penalty, and no power penalty. But we give you this great amount of security. Okay, then comes a little bit of discussion about Chengyen's work. This is analog ICs with flash. How are we doing on that?
5 more minutes.
Okay, I'll try to be quick. So this is Chengyen's paper on FIR filters using flash. This might be of interest to some of us here, right? Because we do some of this DSP stuff. But this is a FIR filter as a workhorse in many DFT applications. The one we implement is the FIR in the direct form, the cartoon for which is shown here. And as you can see, this is a bunch of multiply accumulate operations. So there's these multipliers, as many multipliers as I have taps. And it's basically a multiple constant multiplication problem because the multiplicands are constants. And then we accumulate or add. Question is, can we do this in Flash? And the answer is yes. We use a current mode design. The coefficients that you want to multiply by are stored in Flash. And then, so therefore you have a one transistor multiplier. This gives a dramatic reduction in circuit area and stuff. So let's see how this looks. This is a FIR filter. On the top is just the register chain that's delaying the inputs. And in the middle here, you see these 8-bit FCMs. That's basically our multipliers. And depending on whether the coefficient was positive or negative, the contribution of that multiplier goes to a negative current wire signal or a positive current signal. I convert those currents to a voltage here, and then it goes through a SAR, analog to digital converter, subtract the values of the two ADCs, and that's my final circuit output. All this is this middle portion is done in Flash, the multiplier bank. Okay, here's what the multiplier looks like. You can see one operand is the X's. Those are applied to the circuit. But the Y's, which is the other multiplicand, is stored statically in the Flash transistor. So if you look at this, one multiplier has order n transistors, and an n-bit multiplier takes order n transistors, which is significantly small. That said, here are some of the results. I'll sort of zoom in. We did 3 filters of our 4 filters, 30, 70, 110, 128 taps, both low pass and high pass. And if we look at the results, I'll just sort of zoom into the results on an average. We have a latency hit. So our flash-based FIR is slower by a factor of 2 compared to a digital synthesized FIR, right, of the same precision. So we are slower by a factor of 2, but our power is 4 times smaller, and therefore our energy is about 2 times better, right? And importantly, our area is about 7 times smaller because each of these multipliers does multiplication with one transistor. So it's really efficient, right? And the ENOG, the effective number of bits, should be 9 in this case. We get close to it, 8.87. The limitation of this is if you wanted a large precision, then that would be hard to do because I can't squeeze in that many threshold voltages of, uniquely. So up to 8 or 9 bits, this would work well. We're looking at two more things, right? Like in the next version of this, to improve the precision. That's one. The number of taps we can do arbitrary, but precision to get better, we're looking into that. And the other thing we're looking into is how to do IIR filters. I don't know if you use IIR much, but I haven't heard when we were doing this summer work like 2005, we never used IIR. I think we were using FIR filters, but I don't know if you have a use case for IIR, but we're kind of going to poke around and play with that anyway next. And then there's another ongoing work here with FFTs, but I won't talk about that. It's just ongoing. We probably would be ready with the paper in a few weeks or something. All right, so here's some comparisons with other analog approaches, which were published in 2018 and 2020 and stuff. If you look at this, there are significant improvements are in power per tap, like insanely smaller power per tap. Also, you look at the latency compared to these analog FIRs, right? They're much better. And then also the area, we're much, much better. So basically, there are many metrics that we beat the competition on. Then we'll talk a little bit about regulators. This is among the kinds of regulators that you have for DC to DC conversion. This is something called a low dropout LDO voltage regulator, commonly used for DC to DC applications. Very simple, very compact, and amenable to all digital application implementation, which makes it easy. Makes it popular. So the idea is something like this. You have the regulator that has an input voltage V in. This is its output voltage V out feeding the load. Now the load might have an instantaneous current, which will, let's say, drop V out. Right? When V out drops, it's compared to a reference, and then a controller will turn on more or less transistors to actually feed the current that was demanded. So when more of these PMOS transistors are turned on, a larger current can be supplied. When less are turned on, less can be supplied. So this controller is just controlling the number of transistors, or you can think of these as resistors that are connected to the load. So this is called an LDO regulator. Now the question becomes, well, so what? If you implement this in Flash, what's it going to get us? The important thing it gets us is that with the exact same design, by changing the VTs of the PMOS, the Flash transistors, I can achieve many different specifications of different V out values, V in values, max current, min current, ripple, etc. That becomes a great deal for a manufacturer because a manufacturer basically uses one generic design and they can basically have a product offering, which is 10 different product offerings of different values, so it reduces their cost. That's kind of the gist of where we're going, where we wanted to go with this. And we use something called a pseudo flash implementation. I'll skip through the details of this, but here's the block diagram. Instead of just having one array, we have two arrays, a coarse array and a fine array, right? So the coarse array is just to actually do instantaneous recovery when there's a spike, or to control overshoot and undershoot. And the fine array is just to control the ripple in steady state. So the fine array only is invoked when we're close to steady state, sometimes. Each of these arrays has a separate control unit and a comparator bank and so on. I won't go through the details of the finite state machine for the controller. I'll sort of skip that. We'll go to the results. Here's some results. Among what we see here is like our LDO can, if you look at the different values of voltages it can operate from, right? It's kind of like a large range. It can operate from an output voltage of 0.7 all the way to 1.7. So it's a 1 volt range of possible outputs you could do. So the same chip, they could offer so many products with just by programming them with different VTs. So this basically is a key contribution. And then if you also look at the overshoot, that's VShoot, TREC is the recovery time. Sorry, I keep forgetting to zoom in here. the recovery time or the ripple. These are all competitive numbers with the competition. And the next slide shows the comparison with the competition. As you can see that, we have a large range of possible values that we can use. The competition is not able to do that. And also our area is quite small compared to the competition. So these are competitive, they're pretty useful. Finally, a really quick thing on algorithm accelerators using CNNs, convolutional neural networks. There are some papers on that. The idea here is basically we take this quantized neural network where the activations are 1 bit and the weights are multi-bit, right? We implement it using this bridge type structure where each ln, if you each input in ln, it shows something like this. There's a flash transistor at the bottom, which we program to essentially which carries the weight. So basically, in a neural network, all I'm doing is it's a large inner product. It's like a WI XI. So the WIs are stored in the flash transistor, and the XI it either turns on turns on the current to a positive branch or to a negative branch. So we get a differential performance and therefore an improved accuracy. So we implement this with something like 9,000 activations, and the weights are 8 bits. These are programmed in the flash register. The layout is very compactly done. All the inputs flow in the horizontal direction. You can see these 9,200 inputs just flowing in the X direction. So these are at minimum wiring pitch, so the circuit is really dense. And similarly, the outputs, we have multiple neurons that we can compute. In a layer, you might have, like in our case, we have about 4,000 neurons. So the neurons are, in this case, in the vertical direction. So the outputs of the neurons come out vertically, the inputs go in horizontally. The next layer will basically permute this. So they'll switch between horizontal and vertical. So the layout is really, really densely structured. One slide to sort of express the results. I guess I won't go through the slide. It's just really busy, but I'll just explain the gist of the slide here. So essentially what we did is, with this, we have a lot of knobs again that we can vary because this circuit is almost too fast, okay? Because it's so fast, I can slow it down and reduce the power. That's kind of what we do. Because when we run it really fast, it is high power. And it can do an entire neural net, entire deep neural net on a chip, which nobody can do so far. But it's high power. So to drop the power, we actually reduce the throughput. We force the throughput to reduce. And so we have these knobs that sort of try out different variations of, the sharing of neurons and sharing of layers and so on, and basically trade off power versus delay in some sense. Now, when we do that and we compare it with a state-of-the-art QN that was published recently, and what we see is that despite all these changes, our latencies from 15,000 to like 450,000 times, almost 500,000 times better than the existing approaches. The existing approaches, the problem with them is they're not that dense. So essentially they have to, schedule the computation and, do a portion of the computation, store the results, do another portion, store the results, and sort of cycle through this. There's a lot of memory and a lot of, bit banging going on. But here in our case, the design just flows through in one pass, right? It's just basically clean, completely clean. Nothing needs to be stored. So we are dramatically faster and dramatically better energy, but our power consumption is a little higher. And, and the reason for that is the entire QNN is in a chip. So what you're going to do, you have a larger power consumption. That said, we have a paper that we have come out. Hopefully, we're going to submit in a week or two that addresses this and reduces the power consumption quite significantly also. All right. Finally, a little bit on future work, right? On the digital IC front, we're exploring, and this is with Xiaowei, we're going to explore non-FTL approaches. The thing I don't like about the FTL is it's an analog circuit. It's basically this current mode circuit, which is measuring currents, and just makes it a little less reliable, in my opinion. Pure digital would be nicer. So we are using, another approach we call the ladder approach. Won't get into the details, but that's something we're exploring. Also, we're looking at a better security metric for us, for the secure circuit design. On the analog, we're working on FFTs. I think I told you that, and that's probably something that will get published relatively soon. On the algorithm accelerators, we're working on CNNs with more precision, on spiking neural networks as well. And then also accelerators for graph algorithms. And then, of course, if no talk today would be complete without a mention of ChatGPT. So we're contemplating ChatGPT on a chip. I think I have some thoughts, except I don't understand the internals or the algorithmics of ChatGPT enough. So I'm kind of soliciting some of that input from our communication colleagues and there's some ideas as to how we might do Flash-based ChatGPT and do it in a very, very dense manner. Whether we can actually do it on a chip, I'm not quite sure. But this is early, speculative work at this point, right? What I didn't cover because of time constraints is we can do a Flash-based stack. That was Kyler's thesis, actually. And then also a digital binarized neural network, something we did with Arizona State, and then in-memory computing with Flash in DRAMs. So this is basically what we got. Thanks for your attention. Here's my email address if you be in touch for any details in the papers and stuff. But in summary, this is just this technology we accidentally forgot. And I think that the reason for forgetting this is because Flash is done well by just a small handful of companies in the world. Like there are some companies in the Far East and Micron and stuff. And their fabrication lines capacities are so full with just keeping up with Flash memory chips that they have no time to look at this. Therefore, academics have never really explored this at a circuit level. And that's sort of why I think this thing fell through the cracks. And I think it's an opportunity that we've been missing. And I'm hoping that we have some grants that are in the pipeline and some of which will allow us to fabricate some of these ideas. I'm hoping to do that and actually prove this in silicon. Thank you for your attention.
Nice talk. And any comments or questions?
I have a question. I'm going to pick on your ChatGPT, putting a large language model on a chip. Are you suggesting you simply implement it just in like forward prediction mode, or okay? So you're not talking about, and the same with the CNNs is that you can't train and backpropagate.
So great question, right? This is a perfectly pertinent question. So the CNNs we've presented, they're only inference, they're not training. ChatGPT, I couldn't do training, I could only do inference. And why is that? One key reason for that, right, is the training needs you to overwrite weights. My weights are stored in Flash. And what I didn't mention is Flash is quick to read, but to program, remember, we said we have to apply these pulses and we have to do this iteratively. So programming takes a while. Programming in a Flash memory takes in the microseconds, right, which is glacially slow, right? So, for VLSI, it's very, very slow. So programming is not something I can do. So if I have to update weights and I have to do back propagation, update weights and stuff, that would make things too slow. So the ChatGPT I contemplate to start with would just be a inference engine. Similarly, the CNN's an inference engine. Now that said, we have an NSF proposal out right now where we are trying to do the learning also on the on chip. It's more convoluted. I won't get into great details, but essentially what we're doing is when we do back propagation, the weights we would store in DRAM or something which we can write at the same speed of operation as the rest of the chip. And then every 10 cycles or something like this, or every 100 cycles, we'll program weights into the Flash, basically do this lazy upgrade, lazy propagation of weights in some sense. So we would do something like that, or schedule the updates of layers at in a staggered manner. So while one layer is being updated, the others are using their own weights. So we're going to try some tricks like that to see if we can do training as well in the same flow. But that's a good that's a good question.
Inference mode is good too.
Inference mode is good. One of the other things in that proposal is we said, there are certain reinforcement learning algorithms that they do what they call as one-shot learning or something like this, which is basically you have your weights, right? Which you just download, right? Like a bunch of weights. And then you just do a few iterations of learning and just update the weights and customize or something like this. That's something that's amenable to what we have, because that is not it's not training dominated, but you just do a few cycles, a few rounds of training. That could be something. That's something we're targeting in that sort of new proposal.
I just have one question that goes back to beginning sort of things that drove you into this. And you were talking about manufacturers being able to do speed binning.
Speed binning.
Yeah. And then so that's an advantage for them. They can sell higher price for stuff that they've made faster. But then the other advantage you say present is basically the same thing, where people who have an older chip that's getting slow, say, oh, I'll speed it up now. What prevents people from doing that from the beginning? I'll just buy a slow one and speed it up.
Sure. What prevents them from doing it is that they have to know the exact amount, the exact threshold voltages for all the transistors in the FTL designed in the chip. That's the consumer has to know that. It's extremely hard to know. It's extremely hard to know. So therefore, it's like if you look at let's look at this. Show you this. The cartoon I had for where was that cartoon? So yeah, there we go. So this cartoon, right, is how my chip would be fabbed. Yes, sorry, the one on the right. Yeah, there we go. This thing is how my chip is going to get fabbed, and you're saying, well, the person who purchases it, they're going to go to these black boxes and then going to like reprogram them and make them faster and then, like subvert my speed binning.
Well, I'm just thinking in terms of using it as flash, not even.
Yeah. The reason why it's hard to do, A, there are too many of these. B, the manufacturer won't necessarily reveal to the consumer how you program them. That's B. And C, even if they reveal how you program them, they must reveal what the threshold voltages of each of the transistors in this FTL cell, and there are many of them, are, you see, because as we saw if you saw here, right, like there are like in a 5-input design, there are like 10 flash transistors in a 5-input FTL. So they need to know the threshold voltages of 10 times the number of FTL cells. What should they program to get that advanced speed? Very hard. Only the manufacturer would know that. That's what would deter a consumer from doing this programming themselves, right? So unless the manufacturer told you what to use for those VTs, you simply couldn't divine that information, if you will. So that's basically how it's hard to do that. And that triggered another kind of idea. Oh yeah, that triggers another thought, which I've been proposing to our defense friends, right? Is the advantage of a design like this is, let's say I have a chip that I've manufactured and I've and it's in my secure product, right? That it has all these VTs programmed. For some reason, this gadget that it is in gets in the wrong hands, right? If I know that the gadget's in the wrong hands, I can program all my flash transistors to a blank state, to an erased state. And now this chip and this gadget is useless to my adversary. So it's like a kill switch, right? You have this kill switch, which basically you work the kill switch. It basically erases out all these flash, all the VTs of all my flash transistors. This chip is silicon. it's just a piece of silicon and no more, right? It's completely inert, and that's something they like a lot. It's like this. You can have a supercapacitor on the chip, which when it detects some event like this, goes and flashes out, it goes and programs everything to a blank state. So that's kind of a cool. And the good thing is when I get this thing back, I can reprogram it and it's functioning, you know.
Yeah, that's basically the secure erase they have now, on flash devices.
Yeah.
You tell it, just don't make me set everything, just do it all. at once.
Yeah.
2 seconds later, it's.
It's just blank. Yeah, correct. It's all erased, all erased potential.
So that addresses counterfeiting too, then.
In what way?
Because if the manufacturer doesn't know how to program the device then it seems like you can program it when you receive it.
Yes,
So then they can't be building chips that
exactly.
counterfeit and replicate functionality if they don't know what it is.
Absolutely.
Yeah.
So you're completely right. So they can manufacture tens of these on the side, but they don't know what to program it with. And so that's just completely useless. And for them to know what to program it with, as we saw, right? That complexity is insane. It's basically more than the number of atoms in the universe, like times many powers of 2, right? So it's just basically really hard for anybody to reverse engineer this. So that's this matrix. So if we use L7 or something, right, there'd be 2 to the 763 guesses before they know what to program it with. So they have this counterfeit that they can't do anything with.
You mentioned about the FIR filters. Is that only a paper design, or do you design a chip and test it like that? What is the status of paper design? How hard it is to design something like that and look at
It
it?
needs, so that's a good question, right? Like any of these things, right? All of these are paper designs.
I see.
If you were to tell me, hey, can we actually build a chip to validate this? That would need funding.
Oh, okay.
Our latest NSF proposal asks for funding to do a fabrication.
Oh,
excuse me.
How big is that kind of funding level? Is that 10K? Is it 100K? How big is it? funding
100K ballpark
to
or
do
less.
this kind of design like that? Yes.
So if we do one spin, it depends on where we do the spin and how flexible those spin,
Okay.
those the foundries are, right? But it can be from the high pain amount is 10K, the less pain amount being the 200K. Yeah, so we are like soliciting funding from the defense folks to see if they can foot the bill for some of
Good.
this.
Seems to be
I
for
really
me.
want to fab this.
For me, it looks like that, given that AI and CNN, so what Matt's asking, that seems a very big art area here to make it faster, more customized chips, like a lot of applications there coming up with that.
Right.
And if you could, of course, back propagate another thing, a lot more. You see, neural networks are so variety of that. So many,
Yeah.
a lot of capacity there.
Correct. And what I didn't mention, now that you brought it up, it's a good thing because the CNN that we did, it's basically like an architecture. It's not really hardwired for a certain size, like the layer widths and the number of layers. So you can adapt these. You see what I'm saying? So like if your favorite CNN has, 5 layers and 400, the layers are 400 wide, you can use 400 of of those neurons, or you can do more up to a certain max that we have provisioned. And that max that we provision is quite large. So basically it can be used to implement any existing neural net architecture that we found. So it's actually quite flexible. So it's kind of like in a coarse way, right? It's like an FPGA that it can implement any functions up to a certain size and you fill it up to what it's provisioned in some sense. So it's provisioning a certain number of layers and a certain size of layers. Up to that, you can do anything you want. And that's, I don't know if Kyler is in this call, I don't know, but that's Kyler's work. So he's good. He's the guy who's doing all the CNN stuff. Good. Very good. And he's interning right now, so that's probably why he can't attend.
In terms of cost to fabricate, is it comparable to traditional CMOS?
Good, a super question, right? So Flash is a handful of processing steps in the recipe more than traditional CMOS. So in other words, you do your CMOS processing, right, at the foundry, and then a few more steps are needed to flashify it, if you will. So it is more expensive, but not, insanely more expensive, just a handful of layers. So 5-10% more expensive, or something. Which is also why, like, this has existed forever. See, this is what excites me about this technology, because there are many other technologies they talk about, like tunneling diodes, quantum tunneling diodes, and they're talking about, like the resonant tunneling circuits and so on. And all these are boutique, academic circuits. They can make 1 transistor, 2 transistors from carbon nanotubes and stuff. Flash is yielding. I mean, come on, the people building this, our entire industry built on it today, correct? So all we're doing is repurposing that for something like this. So it's eminently practical, right? It's the production capability, the volume capability is understood and mastered today. Whereas all these other things are, lab sort of curiosities, right? Like they can make 2 transistors and then write lots of paper and then that's it, So that's what excites me. That's why many people have said, why don't you adapt this to, to carbon nanotubes or to these exotic technologies? Because it's easy to fund there. It's easy to fund because there's sort of, curiosity. I mean, it's cute, right? But I refused. I said, no, I want this to be real. Right? I want to underscore that this is a technology we have today, and we could be using now, so that's why I sort of, unyieldingly stayed at this flash thing rather than move to some of the other technologies.
Thank you.
Thank you,
folks. Thank you
Thank
very
you.
much. That's very informative, quite useful.
Thank you so much. And I'll be happy to talk more if somebody has any questions.
But we'll be here tomorrow afternoon, I believe. It will be one more day. He sits close to, where the Scots will
Yeah.
next room.
Scott, right?
Yeah.
We almost ran into each other.
You guys, thanks.
Okay, could we meet after half an hour or something like that? Depending upon schedule and Adam and maybe just for 30
One
minutes. See your schedule because you just came in.
Yeah, I don't remember.
See, now it's about what, 2:45,
Yeah, I'm free.
3:15. Is it okay? Take a break and we can come back and meet. Is it okay? 3:15. Yeah, we can meet in the other room if it's open. 21, 24, smaller room. Okay.
I have 2 questions.
Yes,
I might be
yeah.
too esoteric for general consumption, but
I'll end the meeting here, is
can
that
you
right?
lower the threshold voltage?
Oh, let's do that. Yeah.
What does that do to the noise immunity of your?
So lower threshold voltage increases speed, increases power. Power goes up, speed goes up. And when you say noise immunity, you mean on a digital noise immunity?
Well, I mean, ultimately, yeah, because noise could trip
Right.
throw you over the threshold and give you a state that you're not really wanting to get.
Correct. So the noise immunity doesn't get any worse than in a pure CMOS design. That's kind of one way to characterize it. So in other words, it stays very high.
So you don't lower VT below what a normal CMOS circuit would do.
I could, but I usually don't.
Yeah, okay,
Yeah,
that makes
that's
sense.
perfect.
Because
But
that would be
I get all kinds of ability. I mean, I have a large range I can play with. So
right.
So probably you want to lower it, but then if you have a lot of variation, then you can't lower it any further because some of them will be too low, right?
Yeah. And too low is a little bit dangerous because the transistor is always on, and that's what reduces your noise, right?
Mhm.
We are getting too close to zero, we'll avoid. So what we'll do is, right, we'll carve out a band, say like
Right.
we'll let the VT, and when we're choosing that band, on the high end of the band, we go nuts, right? We go as high as you want. But on the low end, we cap it at like something like 200 millivolts or something like this. A normal chip will do 200, 250, 300 millivolts. So we'll give just a little bit below that
Mhm.
to stay, like fast, but not low on noise and power and stuff.
And is the FIR filter, is it linear phase like a normal FIR filter would be?
You mean, and that would have to do with coefficients, right?
Well, I think FIRs are inherently linear phase if they're done in the digital domain, but I'm worried about. Sorry?
It's all in the digital.
Oh, because I thought you were basically setting the coefficients by varying the VTs.
Correct. Yeah.
Yeah, so
But effective.
I mean, the output's digital, but what's going on under the hood is all analog.
Correct.
So, yeah, what I'm wondering is,
Yeah.
would there be, non-linearities caused by the switching of the transistors that would result into
Yeah.
a
So-
phase?
There
issue.
would be non-linearities if I try to run it too fast.
Okay,
But I run it slow enough that all the transients settle before the next input is
okay,
applied. So the delay of this thing, right, is or the latency is
Mhm.
set to a value where all those non-linearities subside.
okay.
And it's agnostic to the weights you use. So you can choose any weights you want. We don't care, right? As long as they are within that the range we support.
And it would be essentially reconfigurable
Absolutely.
to a point.
Yeah, to a point where up to the number of
100K
taps,
or whatever.
up to the number of taps.
But also then you only have so many reprogram cycles, right?
Oh, yeah.
So-
But that's not.
And it's not really a practical limit. Yeah, it's not a practical limit.
So we wouldn't advise doing more than like maybe low thousands of complete reprograms.
But could you keep it in the analog domain and have an analog output that's proportional?
I'd be happy to do that. It'll reduce the cost.
Yeah, but because,
You know.
I mean, that's kind of, I could think of for certain applications, because you can't really get an analog filter that has linear phase
Okay.
over the entire,
Range.
yeah, but yeah,
I see.
so.
Interesting.
I will end the recording. You will get the Google Drive. Recording will be in Eric's Google Drive.
Oh, really?
Okay, then you
Okay.
can send it to Sunil. That's what it says here.
Yeah.
Okay,
Okay, I'll end
I'll
it.
wait for the email.
Okay, it will send you automatically with since you are the organizer, I guess. And
Lucky
Perfect.
me.
that's why I couldn't add anyone. I thought you were organizer. Then somehow they came in, admitted that I could have been done that. It's not a big deal.
Okay.
Now we know how to do it because everything is ting, ting, ting. It's a,
Yeah.
not a big deal.
Good.
Thanks,
So
Eric.
I looked into it like up to 100 mega samples per second, 16-bit tags, ADCs, and
Mhm.
right? They're not that expensive. Up to 100. I think Adam said you need up to 20 mega samples or something. So
Mhm.
I have a feel. I want to. I have lots of questions for you guys. I will talk about them shortly.
In half an hour,
Yeah,
15
yeah,
minutes,
but
right? Let's take a
Along
break.
the lines of like doing this sort of panel at a time design, right?
Mhm.
Which and then seeing how it might be much cheaper than what we have. I think. Something I things to think. Questions for you guys, right?
Yeah, and.
To-
yeah,
Okay.
absolutely.